So before we start something new, I want to review one thing we talked about last time, because I actually made a mistake in the calculations, but also talking with people afterwards, I realized that there was a point that kind of didn't get across that was worth making. So, thinking about the ratio of we were talking about how much stronger the electric force is than the gravitational force, and we were taking a ratio of forces between two objects. And I think the first thing I said wrong is that I said protons, but then I used the mass of an electron. So let's say electrons. So we want the ratio of the electric to the gravitational forces, and so we just take the magnitude of the forces. So we have 1 over 4 pi epsilon zeros. This is the Greek lowercase epsilon, and then it has a subscript 0, which is why it's called epsilon 0, times q1 times q2 over the magnitude of r squared, absolute value of that, divided by g times m1, m2 of the magnitude of r squared. So what things are the same in these equations? So we're talking about two electrons separated by some distance r. It's that 1 over r squared that's the same, right? And so actually, these cancel. And that already tells us something, which is that no matter how far apart these particles are, the ratio of the forces is going to be exactly the same. So they get a lot closer. Both forces increase by the same amount, so the ratio still stays the same. So the ratio is independent of how far apart they are. And so what we're going to have is a 1 over 4 pi epsilon 0, absolute value of q1, absolute value of q2 over a g, m1, m2. And let's calculate, let's just do the calculation right using glow script. So we have g is equal to 6.7 times 10 to the minus 11th Newton meter squared per kilogram squared. We have 1 over 4 pi epsilon 0, otherwise known as UFPES, equals 9 times 10 to the 9th Newton meter squared per coulomb squared. We have the mass of the electron is 9 times 10 to the minus 31 kilograms. We have the charge of the electron is equal to a minus 1.6 times 10 to the minus 19 coulombs. And so the ratio is equal to 1 over 4 pi epsilon 0 times the absolute value of, called it QE, times absolute value of QE divided by G times that shouldn't be M3, that should be mass of the electron. Mass of the electron times the mass of the electron. So that looks right, right? So print. So does this equation look like the one we've got down here? Looks right. Okay. So if we print the ratio, we actually get 4 0.3 times 10 to the 42nd. So now this ratio is going to, I mean, if we had done protons, it would have been a little bit smaller, right? Because the mass of the protons is bigger, but not that much smaller. So it's still huge. But I think a key thing to notice is that this is independent of separation. Because since they both have the same distance dependence, they get stronger and weaker by the same amounts. Oh yeah, so questions about, yes, Charles.
If you know the electric force, you know the gravitational force, even if you don't know their masses, essentially?
No, because this ratio is going to change depending on the masses. So if we use mass of a proton, so let's change this to mass of a proton. So the question was, if you know this ratio and you know the electric force, could you calculate the gravitational force even without knowing the masses? And the answer is no. So let's do it for a proton is 1.7 times 10 to the minus 27 kilograms. And we'll call that ratio 2. But we'll change this to mass of the proton, and we'll print ratio 2. Okay, so we did the same calculation, and the charge, the absolute value of the charge is going to be the same, right? Because a proton is plus 1.6 times 10 to the minus 19 coulombs. Okay, so if we run that, we're going to get a different ratio. It's going to be 1.9 times 10 to the 36 because the gravitational force is a little bit stronger because the proton is 2,000 times more massive than the electron. But it's still really big. Okay, you have to get a huge amount of mass before the gravitational force starts competing well with electric forces. Yes, Caden?
What would we use the ratio between the electric force and gravitational force for? Like, what would you be, like, what scenario would we use to?
I'm not sure. So the question is, in what scenario would we need to know that ratio? And I can't think of one off the top of my head. So why are we doing this? The reason is just to say gravitational forces are really not very strong. And the reason we think of them as strong is that there's some really, really, really massive objects to keep us anchored to the Earth's surface, for example. Or there's galaxies, there's black holes, out in space. There's a lot of really massive things. But it takes a huge amount of mass to make a gravitational force that's noticeable, whereas it takes a very small amount of charge to make an electric force that's actually pretty noticeable. So in that sense, the electric force is much stronger than the gravitational force. There may be some situation where we want another ratio. Other comments? Yes?
What is the R hat in the gravitational formula?
Well, I was taking magnitudes, right? And so what's the magnitude of R hat? So I should multiply here by the magnitude of R hat, but what's the magnitude of R hat? It's 1, isn't it? So I just left that out because the magnitude of R hat is always going to be 1. Okay, those are great questions. Other questions?
If we have a question like this on the exam, will we be given the masses that we need, or do we prove?
No, you have to prove. If you have a question like this on the exam, would you be given the masses? No, you have to just know the mass of everything in the universe. Yes, of course. It's on the equation sheet that you've already gotten, right? No, you don't need to know masses. You don't need to know charges. You don't need to know the values of constants. This may happen. I mean, you can see that I happen to know them just because I work with this stuff all the time. But you may learn them. But that's not important. That's always stuff you can look up. But knowing the momentum principle, the definition of momentum, the definition of average velocity, how to update momentum and position, that you have to know. So, other questions? Okay, so today to move beyond thinking about point particles and think about objects in the real world that exert. We're going to think about contact forces. So both the electric force and the gravitational force are forces that act at a distance, which is actually a little bit mysterious because these things don't have to be very close to each other to interact. So exactly how they do that is pretty interesting, and that's pretty much the subject of next semester. But a lot of forces just involve contact. So we're going to be talking about contact forces, and to understand them we're going to actually need to understand a little bit more about the structure of the microscopic structure of solid matter. So let me try to convince you that there's a puzzle. So a physics professor stands on the floor. My momentum is not changing, so I'm not speeding up upwards, I'm not speeding up downwards. My momentum is not changing, so we conclude from the momentum principle that the net force on me is 0. So we ought to be able to figure out the force the floor is exerting on me if we know the gravitational force that the Earth is exerting on me, because here's how we'd apply the momentum principle. So we'd say, so when we draw a diagram of an object with forces acting on it, we are used to simplifying the object. So that's a physics professor, and she has a gravitational force downward, and because delta P is F net delta T, and over the next 1 second or half a second or 10 seconds, or pick your time interval, my momentum isn't changing. This is 0, that's 1 second, and so that implies that F net must be 0, so the net force on me must be 0. Okay? So it must mean that something, the floor, is exerting an equal force in an opposite direction on me so that my momentum isn't changing. So we actually ought to be able to calculate the force that the floor is exerting on the physics professor here. So we can say F net is equal to 0 is equal to the gravitational force of the Earth plus the upward force of the floor. And that's, for the purposes of estimating things, let's just say that we'll say that little g, we know it's 9.8 newtons per kilogram, but we're just going to make some estimates here. So let's say it's approximately 10 newtons per kilogram. So we can, and let's say the mass of this physics professor is 70 kilograms, more than it ought to be, but never mind. So we have 0, we have a minus 70 kilograms times 10 newtons per kilogram, 0, plus force by the floor is 0. So we find that we have 0, negative 700 newtons, 0. So we can solve for the force by the floor. Is equal to 0 plus 700, 0 newtons. Okay, a really boring application of the momentum principle, right? Okay, so now we know the floor exerts a force of 700 newtons upward. So now we change the system So we put the physics professor goes away and we put a 10 kilogram raccoon on that spot on the floor. Okay? So we have the floor exerting an upward force which is equal to 0.700 newtons. We have the earth pulling down on the raccoon with a force of 10 kilograms times 10 newtons per kilogram is only 100 newtons, minus 100, 0 newtons. So F net looks like 0.600, 0 newtons on the raccoon. And so in the next second, the raccoon accelerates rapidly up into the air.
That makes sense.
Well, what's wrong with this argument?
Because it's different for each thing based on the force of
What's it? It's different for each thing. What's different?
the force on the floor is different.
So you're asserting that an inanimate object, the floor, somehow manages to adjust the force it's exerting on an object in contact with it depending on the mass contact with it?
Yes.
It's got to be true, but how does it do that? It's a floor. It doesn't have any volition or, okay. So there actually is kind of something to explain here, which is that we deduce from the momentum principle, because we know that the raccoon does not actually accelerate up into the air, surprising all of us and the raccoon. Instead, it stands there on the floor and wonders why it's in a physics class. So really the floor must indeed now be exerting an upward force of 100 newtons, not 700 newtons. But how does it know how to do that? So that's the topic of chapter 4. Now, to understand this, we actually have to come up with a model of the floor or the table or other solid objects or wires that we hang objects from or whatever, and understand what's going on at a more microscopic level to see how this happens. And this leads us into a microscopic view of matter, an atomic level view of matter. Richard Feynman, who was one of the greatest 20th century American physicists, you may have heard of him, once said, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? He said, I believe it's the atomic hypothesis or the atomic fact or whatever you wish to call it. Excuse me. That all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, but repelling each other if they're squeezed into one another. In that sentence, you'll see there's an enormous amount of information about the world if just a little imagination and thinking are applied. So let's see what we can do with this. So the idea is that all matter is made of atoms, at least the kind of matter we're interested in, possibly not neutron stars. That when neutral atoms are a little ways apart, they attract each other. But if you push them too close together, they repel each other. And the atoms keep moving, even at very low temperatures. So let's think about what we know about what a solid might look like at the atomic level. So what are these? These are images of the surface of a solid block of, in this case, silicon, made by an instrument called a scanning tunneling microscope. And there are now several kinds of instruments that can do this. There's something called an atomic force microscope, which makes pictures like this by basically dragging a very, very tiny, low mass needle over the surface of a solid, and you can see that what might look like a smooth block of metal to you at the microscopic level looks like it's made of little spheres. And depending on how you slice it, you're going to get slightly different patterns. So the bottom image is just a different slice through the material, but you're seeing the same thing. We can actually see the atoms that are making up solids now with these instruments. So the atomic hypothesis really is the atomic fact. We can visualize, we can actually see atoms and measure how big they are, the surfaces of solids. So the atoms in a solid object, and we're going to talk a lot about metals because they're kind of easier to understand, because a metal object is made of one kind of atoms, usually, in one kind of arrangement. So it's a simple model. But this model applies to other things too. So here are these atoms. Why do they stay together? Well, there are chemical bonds between them, right? So in a metal, there's actually covalent chemical bonds between the atoms in a metal. And you can see from these pictures that they're arranged in a fairly regular array. Now we've just imaged a surface, so this looks two-dimensional, but these objects are of course three-dimensional. So what we've got is a three-dimensional array of atoms in a solid, and these three-dimensional arrangements are called lattices. And for the purposes of our analysis, we're going to talk about an arrangement of atoms in a solid, a model of atoms in a solid that kind of looks like this. So we're going to assume a really simple arrangement of the atoms, and an atom at each corner of a cube. So that's called a cubic lattice. And we're going to make a model of this object, and a solid object, as if the atoms themselves, these atomic nuclei, the little massive tiny nuclei, and then the inner electrons were little balls, and the chemical bonds were actually springs. Now, interestingly enough, it turns out to be quite a good model. If you think about this system, so here's a copper atom bounded to another copper atom. We've got some 30-odd protons and neutrons in the nucleus. We have a bunch of electrons. All the electrons and all the protons in one atom are interacting with all the protons and the electrons in another atom. This is a very complicated system. But if you actually do the calculations, which involves some quantum mechanics, because those interactions of the, it's basically electric forces. But because these things are very, very tiny, there's a few interesting things that are added to the interactions. If you do the calculations, it comes out that the chemical bonds look like springs. If you stretch a chemical bond, it exerts a force backwards. If you stretch it twice as far, it exerts twice the force. If you compress it, okay, so it actually acts the way springs do. If you stretch or compress this chemical bond, the force is linear in the stretch, just like a spring force. So this turns out to be a very productive model that physicists and chemists use when they're thinking about solids, and it's called the ball spring model of a solid. And this is the model we'll use when we think about how solid objects interact with other objects that are in contact with them. So the idea, the goal of today and a week from today is to understand the characteristics of these chemical bonds modeled as springs. So how stiff are they? How do they interact when you put something, you push down on them? That kind of, so that's our basic goal. To think about that, we have to think, first of all, about how long. There are a lot of balls and springs in a metal object, a lot of atoms and bonds. So we have to think about how long these springs, these little interatomic springs are, and in order to find out how stiff they are. So here is a picture that shows just two of the atoms in that big square lattice we had. And so here's our outer electron cloud, which is overlapping to form this chemical bond. Here's the nucleus plus the inner electrons. Nuclei are really, really, really small. So the radius of an atom is on the order of 10 to the minus 10th meters. The radius of a nucleus is on the order of 10 to the minus 15th meters. So if we drew just the nucleus, we wouldn't be able to see it in this picture. Okay, it's all the mass is there. It's kind of interesting, but so the first question is, we need to find the lengths of these springs so we can talk about relaxed and stretched lengths in the springs. And so the question is, how does the length of this interatomic bond modeled as a spring compare to the diameter of one of these atoms? The electron cloud, yes. When you talk about the diameter of an atom, you're actually talking about the diameter of the electron cloud, because that's sort of what limits how close you can get to the atom. Okay? So we're talking about the diameter of the whole atom. So what do you think? Talk to each other for a second. So what do you think?
Oh, okay.
Okay, so everybody thinks they're the same, which is right. They are the same, because we can see that by, if the bond goes from center to center, to get from one edge of the atom to the other, you go 2 atomic radii. And to get from the center of this atom to the center of this atom, you go 2 atomic radii. So these are the same distance. So if we could find out the diameter of an atom in a solid, then we would know the length of the interatomic bond, because it's the same as the diameter of an atom. Right? Good? Okay. So our goal is to figure out the, and let's not worry about this. Our goal is there are a lot of data out there on solids, and so it's easy to find the density of a solid metal. Just look it up. And the idea is that if we could find the volume occupied by one atom, we could find out the atomic diameter. Why? Well, imagine drawing a transparent cube around one of these spheres representing an atom, and the cube is small enough that the sides of the cube are touching the sides of the sphere, right? So the length of a side of the cube is the diameter of the atom in that case. So if we could find out the volume of one of these cubes, we could just take the cube root and find the length of a side, and that would give us the diameter of an atom. So that's the calculation we're going to do to figure out the diameter of, we're going to use copper. So we're going to figure out the diameter of a copper atom. And what we're going to be interested in eventually, knowing these bond lengths, is things like, what do you think happens if we have this lattice of balls and springs? What do you think happens if we put something on top of it? Why does it exert a force back up? Because the springs are compressed, aren't they? And so, what if we stretched it, hung something from it? The springs would be stretched, right? So these contact forces really have to do with compressing and stretching interatomic bonds. And you can see that I stand on the floor and compress the interatomic bonds in the floor a certain amount. Our 10-kilogram raccoon would simply compress them less. And so the floor would exert a smaller force. So we can see why this happens, but we need to be quantitative about it. So our goal here is to find step one is to find the length of these springs in a real thing like copper. Okay. So the density of copper So now we have a lot of numbers. So the density of copper and this is a thing called mass density, so it comes in mass per unit volume. If you look it up, a number that's 8.94 grams per cubic centimeter. And the atomic mass of copper is 0.064 kilograms per mole. So we need a plan to go from density to the diameter of an atom. So think for just a second about how we might do this. There's more than one way to do this. But take a minute and just talk to each other and think about how we might actually do that.
We know the atomic mass. We can calculate in our object. In that object.
You have to take the
All right, so it sounds like we've got various plans here. So if we have a plan, we start with density, and let's convert to kilograms per cubic meter just because so we're in SI units. What could we get to from that? The number of atoms? Okay, so we really want the number of atoms in our cubic meter, which is that's a lot of atoms, right? Cubic meter is big. So if we get the number of atoms per cubic meter, then we could actually take this quantity and turn it upside down, get the volume of one atom, right? And if we do that, we can just take or meters per atomic diameter, or meters, the number of meters in the side of one of that cube there, right? Basically. Okay, so let's do this. We've got the first 8.94 grams per cubic centimeter. We have to be a little careful in our conversion to SI units. So we definitely have 1 kilograms per 10 to the third grams, that's fine. But 1 centimeter cubed, how do we convert that to meters cubed? Okay, so a centimeter is 0.01 meters, right? So we have to use, so I'm going to say 10 to the minus 2 meters cubed there, right? To get that conversion. So let's actually do it. So we have 8.94 grams per cubic centimeter times 1 kilogram divided by 10 to the third grams times 1 cubic centimeter divided by 0.01 cubed, and we'll call that something. And if we print that, so we get 8, let's use scientific notation, 8.94 times 10 to the third kilograms per cubic meter. Okay, now the next step was to find the number of atoms. So how do we do that? Avogadro's number, yeah. So we have 8.94 kilograms per cubic meter. We want atoms on top here, so we have
times 10 to the 3 on that.
oh, times 10 to the third. Thank you. Yep. That would be awkward. Thank you. 6.02 times 10 to the 23rd atoms per mole, but we haven't converted to moles yet, so let's do that first. 1 mole of copper is 0.064 kilograms, so now we've got moles, right? And now we can have 6.02 times 10 to the 23rd atoms and 1 mole. And so kilograms cancel, moles cancel, and we should come out to atoms per, so this many atomic volumes per cubic meter. So let's do that. We have density times, okay, so atoms per meter cubed is density times 1 divided by 0.064 times 6.02 times 10 to the 23rd. So we get 8.4 times 10 to the 28. So 1 over 8.409 times 10 to the 28 atoms per cubic meter should give us cubic meters per atom. Which gives us 1.19 times 10 to the minus 29 for atomic, we'll put atomic volume here. And so if we take the cube root of that, we're going to get the side of that little cube, right? So d is equal to the cube root of 1.19 times 10 to the minus 29. And how do you raise something to a power in GlowScript? In 2 stars. Okay, so we actually have the diameter of a copper atom. We get D is equal to 2.28 times 10 to the minus 10 meters. Okay? So, very good. Now, what we're looking at, though, let's consider if we're stretching a wire. So let's talk about hanging things on a wire and stretching it. So our wire kind of looks like that. It's all these chains of masses and springs. And so if we hang some big mass from a wire, we're going to stretch these interatomic bonds. So let's think about that. Let's think about that. So down here, this guy, an interatomic bond, has to hold up the block. This next bond has to hold up the block plus these two atoms, right? So it has to exert a slightly larger force, and then this one probably needs a slightly larger force. So exaggerated, we should get really different stretches. Now, probably the mass of the wire is so small compared to the mass of the thing we're hanging from it that this is a huge exaggeration, and it's going to, but nonetheless. So what we're interested in is finding out the stiffness of these things, how much they stretch. And to do this, we've got all these springs. We've got lots and lots of springs, and we want to find the spring stiffness of one of these springs. So how are we going to do that? So, problem, find the spring stiffness of one bond. And to do that, we have to think about what happens when you chain lots of springs together. We have some springs here and some masses. So here are two pretty much identical springs. And here's a third. Let's see if I can unhook this mass. Well, that's all right. We'll use this. So I hang a mass on the spring, and the spring stretches a certain amount. And we get the spring stiffness from the stretch. So let's be quantitative. I would like to get this off because we could use a bigger mass. Here we go. We'll use a slightly bigger mass to, there we go, that's a much better stretch. Okay, so the relaxed length of this is 10 centimeters. Conveniently. Okay, it's not 10, I lied. It is 11. Okay, 11 centimeters. We hang this mass on it, and everything falls off. Okay. Plan B. We hang this mass on it, and now its length is 15 centimeters. So how big was the stretch? 4 centimeters. So so what should happen if amount of mass, but I hook these two springs together? So what should the, not counting this piece, which is not gonna, what should the stretch of this whole thing be if I hang the mass from it? So 4 centimeters is a possibility. What are the other ideas? 6, 2, we got 2, we got 4, we got 6. Okay, so let's see what happens. It's right now this is 10, 20. Can't count from there. 10, 27. Yeah, 27 centimeters long. That's more than 4, isn't it? Definitely more than 4. So let's see what it was. 10, 20, 30, 40, 50, 40, wait, let's see. 10, 20, 30, 40, it's about 40, yeah, it's about 40 centimeters. So, what did we get?
It was 27.
It was 27.
Originally.
Yeah. So I'm guessing these springs aren't exactly identical. So we got something like 13, but it's certainly more than 4, isn't it? So if they were really identical, which I think they're not, think about what should happen. This spring is holding up the mass, this mass, so it should stretch 4 centimeters, right? If this spring were identical, it's holding up pretty much the same mass, so it should stretch 4 centimeters if it were really identical. So the total stretch ought to be something like 8 centimeters, shouldn't it, if these were really identical springs? So basically we made a softer spring. So what happened to the spring stiffness of this thing? If we put 2 springs in a row, the stiffness went down, didn't it? So springs in parallel, I mean in series, so we call this series, so springs in series, spring stiffness goes down, doesn't it? So when we have a chain of, we have a long chain of springs like we have here, if we have 10 springs in a row, the total stiffness should be something like a tenth of the stiffness of one spring, right? So the more springs we stick together, they all stretch the same amount, more or less, and we've got a much bigger stretch for the same force. Okay. So what if instead of doing that, we put these springs, what we're going to call in parallel. Okay, so when I hang this, use both of these springs if I can to support these masses. Stretch looks like less than 4 centimeters, doesn't it?
Yep.
Yeah. Looks like something on the order of a little over, something like 1.5. So if the springs were really identical, it would probably be 2, right? So if we have springs in parallel, the spring stiffness, the stretch went down, so the spring stiffness must have gone up, right? So if we can find the stiffness of if we hang a mass from a wire, the idea is if we can hang a mass from a wire, we could find the spring stiffness of the whole wire. Then we could say, well, we know how long these atomic bonds are, so how many bonds were there here in this wire? we can count the number in series, we can count the number in parallel, and we could find out the stiffness of one interatomic bond, which we don't quite have time to do today, but we will do next time. So just to solidify this, so you hang a 1 kilogram mass from a spring, which stretches 4/10 of a meter. Then you make this series chain. Now we've got springs end to end. If the springs are truly identical, which ours aren't, yes?
When it says how much longer does this longer spring stretch, the longer spring, does it mean both of the springs together?
Yeah, so what I was trying to measure was the distance from the top of this spring to the bottom of the other spring, assuming that this piece in the middle didn't stretch at all, but let's pretend that piece in the middle is really small, so they're just, so yes, basically the springs in series considered as one spring is the question. Okay, so do you want to, okay, you got an answer? Let's see what your answer is. Yeah, okay. So it should stretch twice as much, right? So 8/10 of a meter. Right. And if we, so now if we talk about spring stiffness, if we take a spring that has a stiffness of 20 newtons per meter and put 4 of them in series to make a longer spring, what is the spring stiffness? And let's remember all right, so okay, so you got an answer? Okay, so we've got twos. So how do you think about it? If we have to get the same force, we had 4 times the stretch, so we had to have the spring stiffness over 4 to get the same force, right? So we can generalize and say that for n springs in series, I'll call it the effective spring stiffness is the spring stiffness of one spring divided by n, right? So so what about n springs in parallel? the original spring stiffness times N. So it goes up. Okay, questions about that? So next time we'll use this to actually figure out the stiffness of the interatomic bond in copper modeled as a spring. Questions? Yes?
So is like spring stiffness basically like the amount of spring is going to stretch?
Well, remember that the units, so what is spring stiffness? Is it the amount it's going to stretch? Not exactly, because remember what the units are. The units are newtons per meter, right? So it's how big a force you have to exert to stretch it a meter. And if the spring stiffness is smaller, that means you have to exert a smaller force to stretch it a meter. Okay, I know you're all dying to have a quiz. Really excited about this.